For our engineering design project, Kevin Smith, Kunal Upadhyay, Louis Jensen, Matthew Janes, and Megan Gendergeski all worked on a trash trap for Ellerbe Creek.
The Falls Lake Reservoir provides water to 470,000 members of the Raleigh-Durham area. The problem is that the tributaries to the reservoir are extremely polluted, especially Ellerbe Creek. Our clients, who are members of the Ellerbe Creek Watershed Association, have tasked us with making a device that removes surface-level trash from the creek. The request was broad, which gave us a lot of leeway when devising solutions to the problem.
This project will be advantageous in three main aspects: human, environmental, and legislative. Removing this trash will improve the drinking water for the citizens of Raleigh, North Carolina. It will also minimize the impact the pollutants would have on the flora and fauna. Another important purpose of our project is to collect data on the type and amount of trash that flows down Ellerbe Creek.
Our design was made up of three primary design blocks: the cage and surrounding net, the wings, and the attachment to land. The cage was made up primarily of 2-inch PVC, chosen for structural support as well as the amount of buoyant force the PVC would provide. It was made to be 75 inches by 53 inches by 32 inches, in order to reduce the probability of the device tipping. The PVC was connected at the corners using three-way joints, while T-joints were used to create the two support bars on the bottom of the cage. The cage is stabilized in the water by 3 sections of pool noodles, which provide enough buoyant force to accurately define the plane on which the cage floats. These sections are made up of pool noodles inserted onto 3/4-inch PVC pipe and were connected to the main cage using 4-way joints and T-joints connected to reducers. The cage also has ankle weights attached to it in order to cause the cage to float at the proper level. The net was attached by using metal hose clamps to fasten the net onto the frame of the cage. The wings were also made using the same method of inserting the pool noodles onto 3/4-inch PVC pipe. The wings consist of 2 of these types of pipe, with one standard 3/4-inch pipe meant to be underneath the surface of the water. Overall, the wings are 61.5 inches long and 7 inches tall. This allowed the device to divert and capture the maximum amount of surface level trash, including trash at slightly below surface level. The length of the wings also allow the trap to cover the majority of the width of the stream, which was about 15 feet at normal height. These wings were connected to the cage using T-joints and a 2-inch to 3/4-inch reducer. Finally, the attachment to land consisted of 1/8-inch airplane cable connected to the 2-inch pipe. It was then placed inside of a garden hose and wrapped around a tree in order to prevent that tree from growing into the cable. The cable is about 24 feet long as of now, but will be cut to specification on site. 2 design features were the height of the trap in the water and the multiplicity of the attachments to land. The bottom of the trash trap lies about 6 inches below the surface of the water. This was done in order to allow the device to collect trash at slightly below surface level, in addition to collecting trash at surface level. The multiplicity of attachments to land was done in order to provide some redundancy in case of a failure on either cable, as well as to reduce the stress on either one cable. One key design decision was the decision to not have any attachment to the bottom of the stream bed. This was done because Ellerbe Creek has widely varying heights at different times, and therefore it was important for us to allow the device to move up and down with the height of the water. Had the device been attached to any fixed point on the stream bed, this would have been impossible. So we decided to make the device buoyant so as to automatically cause it to lie on the surface of the water. This sped-up test demonstrates how the trash trap works. The trash is funneled towards the central cage by the wings, and the netting and cage combine to contain the trash. The whole system is powered by the flow of the water, but because Ellerbe Creek only flows in one direction, downstream, this acts in our favor to provide an easy way to drive trash collection.
Through testing, our team has found that the device is capable of capturing over 90% of surface level trash. This percentage is much higher than what we set as our minimum. We used PVC and polyethylene foam noodles to build our device. In terms of device security, we will be attaching the device via airplane cables wrapped around trees. All of these materials were found to be strong and long-lasting. These materials were also cheap, which allowed the team to stay far under our budget of $3,000. The device was designed to be accessible. By leaving the top open, volunteers will be able to easily access the trash collected, allowing for easy analysis of the trash. Our device will also be portable. Our team decided to leave off one of the wings and instead assemble it on site. This allows us to place the device in the back of a 6x8 pickup truck, allowing for easy transportation.
Our design had many strengths. Most importantly, it collects trash very efficiently. The semi-submerged net and large entrance allowed the device to collect all floating trash within the span of the runners. It takes advantage of the flow of the creek to pull trash into the device. Secondly, our device is easily replicable. The highly available and low-cost materials make it easy to build again. If proven successful, the device will be implemented in many other tributaries. Next, the device is extremely low cost. The main material used to build the device was PVC pipe, which typically costs about $5 for 10 feet of pipe. Another strength was that our device was extremely buoyant, so buoyant in fact that we included adjustable weights in case buoyancy needed to be manipulated. The device is also attached very securely to land. We used airplane cable to attach the device to the stream banks, which is easily strong enough to stand up to the flow of Ellerbe Creek. Finally, our device self-adjusts with the water level. Ellerbe Creek is known to have drastic height changes during storms, and because our device is buoyant, it will remain on the surface of the water and continue to collect trash. Our design is not perfect. Some pollution is inevitably submerged. Although it was not part of our task, our device is still unable to collect trash far beneath the surface of the water. Another limitation is that because the creek is trapezoidal and the runners are fixed, the creek cannot be fully spanned at all heights. Even though our device should collect nearly all the trash that flows by it, it does require water flow to collect trash. This may cause some trash to sit in the water longer than necessary before it is pushed into the trap. And finally, our device was so buoyant that we had to add weights to make it float at the right level, making the device itself heavier than it ideally should be. Nonetheless, our device is still extremely successful in all measurable areas.
Our team would like to express our gratitude to everyone that has helped us in the process of making this trash trap. We'd like to give a special thanks to our professors, Dr. Satterbeck and Dr. Santian, our technical mentor, Dr. Schad, our clients from the Ellerbe Creek Watershed Association, our TA, Ryan Briggs, and our lab manager, Murad.